Para mí es un agrado presentar a mi amigo y colega André Vieira, de la USP, la Universidad de Sao Paulo. Él se especializa en físico, se especializa en física estadística, en el Instituto de Física de la Universidad de Sao Paulo. Para los que no tienen idea, la Universidad de Sao Paulo, la USP, debe ser de las 2 o 3 universidades más grandes de Latinoamérica, en cuanto a calidad y tamaño. Pues es una cosa enorme, o sea, es como una ciudad. Es así todavía, supongo. ¿Eh? Entonces, tener contacto con ellos y con la gente allá es muy importante para todos nosotros. Así que, en ese contexto, con André nos conocimos vía otro físico, que es Hans Hermann, en el ETH de Zurich, hace 4 años, 5 años, y de ahí hemos mantenido contacto y hemos trabajado juntos. Y vino por esta semana y nos va a presentar un seminario que figura ahí, el proceso de contacto con el desorden periódico temporal. Sin más, esta es la palabra. Por favor. Son como 40 minutos. 40 minutos aproximadamente.
Olá, gracias. Le agradeço a ele por la invitación. No conocía a Santiago y lastimo que no sea capaz de hacer el seminario en español, pero lo hago muy mal.
Sí. Pero portugués se entiende muy bien.
No, pero
puede pasar a inglés.
Okay. I think I speak English because when we speak about technical issues, it's much easier to speak English. So, the motivation of this work is that when we look at stochastic processes, usually we work with rates which are fixed in time. Okay, but a legitimate question is what happens if you let these rates change as a function of time, and what different effects, different phenomena you can observe when you do that. But before we delve into that, let me say a few words about myself. Initially, originally I'm from Fortaleza, a city in the northeast of Brazil. Beautiful beaches, a nice modern city with buildings, but with the sea, warm weather, and usually a very pleasant environment. But now I moved to São Paulo, which is like that. Okay, and this is actually a picture from a crossing very close to where I live. Okay, and São Paulo is this huge 20 million people city, megalopolis, if you will. But not everything is bad, because the university is quite good, the scenery. This is a picture of the campus at USP. It's a good university. The campus is very beautiful, and Fortaleza and São Paulo recently shared a feature which made me very happy, which is the fact that both São Paulo and Fortaleza are among the cities where Lula beats Bolsonaro by the largest amount of votes. The other one is in Salvador, which is right in the middle between São Paulo and Fortaleza. Okay, this is a map from The Economist, showing the places where Lula won, the places in blue where Bolsonaro won, and São Paulo is a kind of an island among the places where Bolsonaro won. But so much for politics, okay? I couldn't resist that. But so this work has been done with 2 collaborators, Ariel Fernandes, who was my master's student, and José Royos from the Physics Institute at São Carlos, a city in the interior of the state, about 250 kilometers from São Paulo. So, in order to work based on that motivation that I told you, we decided to look at the contact process which is a stochastic process defined on a d-dimensional lattice with coordination numbers here. I'm only working with regular lattices here. So this problem can be interpreted as a model for the propagation of a disease. And the basic dynamics is that, do I have a pointer here? Okay. The basic idea is that each side of the lattice can be one of two states. The zero state, which is interpreted as susceptible, and the one state, which is interpreted as infected. And the rule is that susceptible sites have n infected neighbors, having n infected neighbors can become infected with a rate which is governed by this parameter lambda, and is proportional to the number of infected neighbors and inversely proportional to the coordination number. So the rate at which susceptible site becomes infected is given by lambda times the fraction of neighbors in the infected state. And on the other hand, an infected site can become healed, become susceptible with a rate mu. Okay. For the sake of illustration, in one dimension, the rules of the dynamics can be summarized by this figure here. I don't know why these lambdas and mu's turned into L's and M's, but okay, this should be lambda. Very odd, because in my computer it shows as a lambda. I don't know. This is a susceptible site which becomes infected with rates lambda because it has two infected neighbors. If it has only one infected neighbor, it becomes infected with the rate lambda over 2. And if it's infected, it becomes susceptible with the rate mu. Okay? These are the basic rules in d-dimension, and we can guess how it looks in higher dimensions. But for statistical physics, phase transitions are a very important issue. So this process has a phase transition, non-equilibrium phase transition. When lambda reaches a critical value, which depends on mu and on the dimension of the lattice. But even in one dimension, it has a phase transition. If lambda is smaller than this critical value, this is a picture of what happens in 1D. In the horizontal axis, we have the space axis, and this is the time axis, increasing upward, down, from up to down. And if lambda is smaller than this critical value, we are in an inactive or absorbing phase, in which even if we start with a large number of infected sites, the disease eventually dies out. If lambda is greater than this critical value of lambda, the disease becomes endemic over time. And if lambda is exactly equal to lambda to the critical value, we have this fractal-like patterns which appear over time. Okay, I apologize if I'm preaching to the choir. If all of you know everything about this, but I didn't know exactly what to expect. Are you familiar with this content process? All of you? Okay. So the way to characterize the phase transition from the point of view of an order parameter is defined as order parameter as the fraction of infected sites, and as we vary the ratio between mu and lambda, eventually we have this fraction of infected sites becoming 0 exactly at a critical value, and we can also look at the fluctuations of the number of infected sites, and it has a peak. It's analogous to a susceptibility, and but of course, we're talking about averages taken in the stationary regime after we wait a very long time. We can characterize this transition by a set of critical exponents by looking at how the fraction of infected sites behaves as you approach the critical point. This, of course, is the fraction of infected sites in the asymptotic regime. From this behavior, we can define a critical exponent beta by exactly looking at this scaling behavior here. The susceptibility leads to another critical exponent minus gamma since it diverges. And of course, this is only valid in the limit of very large lattices. The transition is in the universality class of directed percolation in D plus 1 dimensions. There are other critical exponents that we can define. For instance, if we look at correlations between the states of different sites at the same time, this gives rise to this correlation length with an associated exponent minus u perpendicular. And if we look at the states of the same site at different times, we get a characteristic time scale tau, correlation time, which is associated with another critical exponent minus nu parallel. And of course, there are other critical exponents that can be defined from time-dependent quantities exactly at the critical point. For instance, if we look at the critical density of infected sites, how it depends on time, it follows this scaling law here, and this exponent delta can be related to previous exponents, the critical exponents of the other parameter and the critical exponents of the correlation time by this relation here. So far so good. The way to look at the mathematically to investigate these dynamics is to follow the mass equation, the time evolution of the probabilities of the different configurations, and from that we can build the rate equations to investigate the time dependence of the state of a particular site. For instance, if we label a spontaneous configuration by this vector here, where eta is the state of eta 1 is the state of the first site, etc. And of course, eta can be either 0 for a susceptible site or 1 for an infected site. We can write this equation here, which is exact. It says that the time derivative of the average value of eta at the site I depends on the rate of change, the rate of healing, which makes this value goes down, makes this value go down, and the probability that it's infected by infected neighbors. This delta is the sum of the neighbors, and this is where it gets complicated because now we have to deal. If we want to solve this equation, we have to deal with the average value of the product of the variables associated with different sites. And this, in general, we cannot separate. If we try to write an equation for that, we get an equation involving the expected value of the product of 3 operators and so on. So for finite dimensions, this cannot be solved exactly, even at 1D. But if we take the limit of d going to infinity, this can be uncoupled, and we use this approximation, which is known to become exact when d goes to infinity and leads to a mean field approximation. So we can uncouple this, we can decouple this equation in this way, in this limit. And of course, if we invoke translation symmetry, all of the expectation values of the sites become the same, equal to rho, the average value of the average fraction of infected sites, and this becomes solvable and gives rise to this logistic equation written here. It involves lambda, mu, and it's easy to solve. The solution is here. We can determine that the critical point separating the inactive phase from the active phase is lambda c equals mu. And exactly at this point, we have lambda c as a function of t going with 1 over t. And if we look at the neighborhood of the critical point, rho as the asymptotic value of rho follows this scaling behavior, so that those critical exponents which we define below are equal to 1. Both beta and delta equal to 1. So nu parallel also is equal to 1. Many critical exponents become trivial, and this is a picture of the time behavior of these fraction of infected sites. Rho is a function of t. Exactly at the critical point, this is the black curve here. We have asymptotically this 1 over t behavior. Red curves are for the active phase, lambda larger than lambda critical, and blue curves are for lambda smaller than lambda critical, which means that we are in the absorbing or inactive phase. So these are the asymptotic values of rho, which follow this behavior here. Everything is fine. But now we want to look at what happens if we let these rates change with time. Okay, we let them fluctuate. It can be made randomly, but there's a more convenient, there's a more interesting way to look at that based on the facts, based on a heuristic argument for the relevance of this kind of change that I'm going to discuss now. So the idea of this heuristic argument is to look at the stability of the solution under time symmetry gradient. By time symmetry gradient here, I mean simply introducing a time dependence to the rates. Okay. And the heuristic argument works by looking at perturbative time symmetry gradient. We let the rates become nearly constant, but not quite. There's a small fluctuation, okay, and this fluctuation is assumed to behave like this. We quantify the fluctuation by this expression, this function g of t, and we assume that these fluctuations grow with time as time going to the power of omega, and we call this omega a wandering exponent. For instance, if we introduce uncorrelated random rates from time to time, we would have omega equal to 1/2, okay, by the law of large numbers. And the heuristic argument goes as follows. Close to criticality, which means that the distance to criticality is measured by the difference between lambda and the critical value of lambda, which we'll call epsilon, is much less than 1. So we are very close to criticality. The characteristic time scale is set by the correlation time, tau, which in the uniform limits on which we are perturbing the system behaves as epsilon to the power minus mu parallel, as I introduced previously. So over time, tau, the fluctuations are expected to change the local value of lambda c, because we can have rare effects which are affecting the value of the rate. So we also affect the value of the critical value of the critical parameter lambda c. And this leads to a variation, to a change, to a fluctuation of the distance to criticality itself. And this should be proportional to the fluctuations. So the average change in epsilon over a time scale tau behaves as g of tau, which is a measure of the fluctuations, over tau in order to take the average. But these are assumed to behave like, fluctuations are assumed to behave like tau to the omega. And if we work out the relations, taking into account this behavior here, we arrived at the conclusion that the average change in epsilon, delta epsilon, behaves like that. It's epsilon to a power of 1 minus omega times mu per power. Okay. If this quantity is larger than the actual distance to criticality, then we expect that the critical behavior is going to be changed, because we are inducing fluctuations which drive the system quite, which make the system go much farther from the critical point than we want it to be. So the condition for this change to happen is that this exponent omega is larger than 1 minus 1 over mu perpendicular, because that's what it makes. That's what it takes to make this exponent larger than 1. So in the case of the mean field contact process, this condition means that we should have omega larger than 0. So we have a prediction that if we break time symmetry with fluctuations characterized by a alternate exponent which is positive, we should observe a change in the critical properties. And if omega is less than 0, then we should not have any changes to the critical properties. And this can be put to the test most conveniently if we have a way to impose fluctuations from which this wandering exponent can be tuned. Okay? And there's a quite interesting way to do that, because if we only look at uncorrelated randomness, this omega is fixed at 1/2. Okay, so we expect that this critical behavior is going to be changed. This has already been studied by one of my collaborators. But now we decided to look at some kind of fluctuation which allows us to tune somehow change easily the value of omega. And for this we chose a kind of aperiodic sequence generated by substitution rules, okay, with which I guess most mathematicians are familiar. This kind of substitution rules, applications, acting on a finite alphabet. Okay, so the idea is to look at this kind of family of applications which work in a 2-letter alphabet consisting of the letters A and B. If we apply the application to the letter B, we get a letter A, and if we apply this sigma to the letter A, we get an A followed by K letters B. Okay, this is a family of applications which generate aperiodic sequences as long as K is larger than 1. K is always an integer, of course. And for when K equals 1, we have the Fibonacci sequence. We start with a letter B, we apply this rule, we get a letter A, if we apply again, we get this AB, apply again, we get ABA, of course, and the sequence generated is aperiodic, and the number of elements, the number of letters you get is exactly the Fibonacci numbers. So this is why it's called the Fibonacci sequence. And when you go to K larger than 1, you have, if you will, a generalized Fibonacci sequence. In order to quantify the fluctuations, we have to look at the numbers of letters A and B we get after applying the rules n times. And this can be easily done with this matrix equation here. There's a characteristic matrix for every value of K. The eigenvalues of this matrix are, of course, important, and they are given by by these quantities here, and lambda and zeta k plus is the largest eigenvalue, is always larger than 1. It follows from the oh my gosh, I forgot the number of the theorem. Never mind. The name of the theorem. Okay, never mind. It's always easily verifiable for this case. And the second eigenvalue, lambda q minus, has an absolute value smaller than lambda k plus. It's easy to see that the number of letters of either type grow after n applications, n iterations, with the largest eigenvalue to the power n. And with that, we can define the total number of letters. We can calculate the total number of letters after n iterations, calculate the asymptotic fraction of letters of each type. And these turn out to be important in the definition of the fluctuations associated with the sequence. These fluctuations are defined as the difference between the number of letters of either type that you get after n iterations minus the expected number of letters that you would get if the fraction of letters would be the same as the asymptotic one. So this quantifies the fluctuations, and it can be shown that these fluctuations grow with the second largest, the second eigenvalue on the k, zeta k minus, to the power n. Okay, and this can be used to define this Waddell exponent, and it turns out that the exponent is given by this expression here. Okay, and so by changing k, you can change this Waddell exponent and change how you quantify the fluctuations. So this is just a plot of g of n as a function of n for different values of k. If k equals 1, the fluctuations decrease over time. So omega, it turns out, it's equal to -1. If k is exactly equal to 2, you have omega equals 0, like this. This is omega as a function of k. If k equals 2, you have omega equals 0, the fluctuations remain constant. If omega is larger than 2, for instance, if omega is equal to 3, you have these increasing fluctuations as shown here. So according to the heuristic argument, we should have no change in the critical behavior in this case, because omega is smaller than 1, smaller than 0. You have definitely a change in the behavior if omega is larger than 1, for the case k equals 3 or larger. And this case of k equal 2 is undecided because it's exactly at the threshold between relevance and irrelevance for regarding the critical behavior according to the heuristic argument. This is just a curiosity to show that if you want to emulate the fluctuations associated with uncorrelated randomness, you have to choose k slightly larger than 4. So the idea now is to investigate the contact process with an aperiodic disorder, time disorder, inspired by those sequences. And how we do that? We choose the rates lambda and mu from two sets. There are two possible values for lambda A in principle. For lambda in principle, either lambda A or lambda B, and the same for mu, either mu A or mu B. And we choose one or the other, lambda A and mu A or lambda B and mu B, according by looking at by dividing time into blocks of fixed length delta t, and if the jth letter in the sequence generated by the application sigma k starting from a single letter B is A, you choose as rates lambda A and mu A, and if it's B, you choose the rates lambda B and mu B. Okay. It's convenient to define these average values. Average value of lambda over the first L blocks, time blocks, and average value of mu over the first L blocks. And since we are looking at the mean field limits, we know exactly how to solve the evolution equations inside each block. You just have to match the conditions in the when two blocks meet, and you impose an initial condition for the value of rho, and you get a map which connects the value of rho in the end of the previous block with the value of rho in the end of the next block. And it depends, this map depends on these quantities Rj and Sj, which in turn depend on the values of mu and lambda in each block. So this is a map, we can iterate the map. And what we get are pictures like the one I showed in the first slide, and I will show again in a few moments. We can iterate the map to get a map between the value of rho in the end of the jth block and the initial value of rho. These are written as these expressions here, and we can show that the density of active sites is asymptotically zero unless the asymptotic value of the average of lambda is larger than the same quantity for mu. Okay, it's very similar to what we get in the uniform limits, but now this has to be done for the average values. And for our family of sequences, if we choose to change only the values of lambda, to allow only the values of lambda to change and choose mu as a fixed quantity, the critical condition becomes this one here. And it depends on the asymptotic letters of fractions of letters A and B, and the values of A and B that we choose, and the value of mu. If this equation is fulfilled, you are exactly at the critical point. So the kind of pictures that we get is this one. This is a plot of rho of j, which means the value of rho at the end of the jth block as a function of j. So j here plays the same role as time. Okay, so as j increases, time increases, and we get when the rates are lambda a, we assume lambda a to be smaller than lambda b, and this is close to the critical point, so that when lambda is equal to lambda a, rho becomes smaller because the infection rate is smaller than the healing rate. So it's much more probable that agents become that the quantity of infected sites gets smaller, and when the infection rate is lambda b, which is larger than mu, the number of infected sites goes up, and it goes like that because this is aperiodic, so we can never identify a regular pattern for this one. But now we can take advantage of rescaling transformation in order to obtain some analytic results. For instance, we notice here that we could join together these two blocks as they were one single block, in which the effective rate gets a calculable value you can calculate, and likewise for this the sequence of three blocks in which the infection rate is lambda a. And if we do that, we can define another kind of sequence, an effective sequence, which goes like that. And we can then again define effective rates And of course, we have to take into account the fact that the blocks will now have different times. And we can proceed and look at, for instance, take advantage of the fact that in these two blocks, the change in density is larger than in this one. We can join together these three blocks and join together these three blocks and repeat this and write matrix equations for this rescaling transformation and work with them. And from that, we get something like this picture here. And the interesting fact is that if we are exactly at the critical point, this structure can be iterated indefinitely. And it gives rise to an invariant sequence. This sequence of green, this is just schematic, but the idea is that we have a kind of effective block here, a kind of effective block here, here. And if we operate following these rules, we get, after the rescaling, the same sequence, apart from minor boundary problems, we get the same sequence here as we got here. So we can iterate this process indefinitely and write matrix equations to deal with that. And if we try to look at this problem slightly away from the critical point, we notice that we have to stop performing this rescaling after a given time, a certain number of times. And this number of times in which we have to stop because the system is not invariant anymore. It essentially gets to an asymptotic constant behavior. If we look at that, we can calculate how many times we have to, we can repeat this process and work from that, noticing that the size of the duration of the blocks at this step is an estimate of the correlation time, and this allows us to calculate the critical exponent nu parallel, which is the critical exponent, one of the critical exponents of the problem, governing how the correlation time changes as we approach the critical point. And we can analytically determine the value of nu parallel for all values of k. And it turns out to be this expression here. If omega is negative, this yields 1, which is the same value as the uniform case. And if omega is larger than 1, the value becomes 1 over 1 minus omega, which is larger than 1. And this is in perfect agreement with the heuristic argument, which predicted that the critical behavior should be changed if nu parallel was, if omega is larger than 0. So besides looking at the critical exponents, we can look at what we call the geometrical noise, which is the noise induced by the competition between the aperiodic sequence and the dynamics of the model itself. And we can do that by estimating the distributions for the densities at a given time and for the log of the density at a given time. And the idea is to look at the relative noise given by the standard deviation of the density at a given time and the average value of this deviation. This is like the relative width of the probability distribution of the densities. But in order to do that, we have to do the following. Instead of always starting from a letter B, we can build a very large lattice, very large sequence, and choose randomly the initial block for the dynamics. And then from that, as the sequence is aperiodic, every time we have a different sequence, and every time we have different values of rho after a given time t. And so this allows us to estimate those quantities here. The idea to look at both the distribution of rho and of the log of rho, it's because if the distribution of rho is dominated by rare events, the distribution of log of rho would not be. The log usually the log filters extreme values. And so we look at the effect of, we search for the effect of rare events by looking at both those two quantities here. And so let's take a look at the results for different values of k. First, for k equals 1, whose wandering exponent is omega equals -1, we obtain by, if we study the critical behavior and we look at the time dependence of the density, either at the critical point or above the critical point or below the critical point, we have a very similar picture to the one we get in the uniform case, as predicted by the heuristic argument. The critical exponents are the same, beta equals delta equals 1. And we can also look, we can also try to produce a data collapse for different distances to criticality by looking at these free scale plots of the density divided by epsilon to the beta, and as a function of time divided by epsilon to the minus nu parallel. This is just the correlation time, and we obtain a beautiful data collapse if we use the same critical exponents as those in the uniform case. And if you look at the relative noise at criticality for different values of the ratio between lambda A and lambda B, for all values of lambda A over lambda B, we can find a critical value of mu, and we always tune to this value to produce these curves. So what we show here is that the relative width of the distribution of rho, the linear width is finite. It goes to a finite value as t increases, and the relative width of the log of rho goes to 0. So it's pretty much the same results as in the uniform case. But when we look at k equals 2, things start to become more interesting. Because in this case, the wandering exponent is omega equals 0. And different things could happen. Remember that we are just at the threshold between relevance and irrelevance if we have k equals 2, because then omega equals 0. We have the same critical exponent. This is in average a 1/t behavior here. And the value of beta is always equal to 1. But if you look at the critical noise, the critical geometrical noise, something interesting starts to happen. The relative width of the log goes to 0 as time increases, but the relative width of the density itself seems to diverge. So it's a suggestion that the width of the probability distribution of the densities is slowly increasing as the temperature as time increases. And finally, if we get to k equals 3, whose wandering exponent is about 1/3, then things go wild. This is this darker peak, this darker curve here is exactly the behavior at the critical point, and it has huge fluctuations, even if you look at different time blocks. And the rescaling transformation yields this value of the critical exponents associated with the correlation time. Numerically, we find beta in average equal to 1. This delta is also different from the uniform value. And it's much harder to obtain a good data collapse because it has huge fluctuations. But if we take averages of remaining initial conditions, then we can find this kind of behavior here, which is a reasonable data collapse, showing that these exponents seem to be correct. And finally, for the behavior of the relative geometrical critical noise, we get this very interesting behavior that the relative noise associated with the density increases, always increases very, very rapidly, actually with a power law with an exponent given by omega for all values of omega larger than 0. And the relative width of the log goes to a constant. So it means that there's the width of the density goes to infinity, but the width of the log becomes finite. So indeed, there are rare events which dominate the averages, and it gives rise to an infinite noise in the long time limits. So that's it. In summary, we show that sufficiently strong geometrical fluctuations do indeed induce infinite noise, asymptotic behavior, at least at the midfield limits. These results fully agree with the heuristic argument, and we can extend this analysis to finite dimensions, but that requires extensive simulations which are still underway. And with that, muchas gracias por su atención.
Ya sea acá, no sé de dónde se mira, pero pregunta del auditorio acá. ¿Hay alguna de afuera?
Isabel, si quieres puedes hacer la pregunta.
Sí, se puede contactar nuevamente.
Ah, ok.
¿Se puede?
Sí.
No sé si me pueden escuchar.
Sí, fuerte y claro.
Ya, fantástico. Mi pregunta era como súper al principio de la presentación, cuando recién estaba planteando el problema y bueno, los valores eran 0 y 1, así que obviamente solo podían estar como infectados o no infectados. Pero eso
Sí.
significa que quienes ya se infectaron pueden infectarse de nuevo una vez que sanaron.
Sí.
Eso era lo que había preguntado así como media hora, pero quedó claro después, así que gracias.
Sí.
Gracias. ¿Hay alguna otra pregunta en ese lado?
No sé si creo, no, al menos no sé si hay más preguntas de las casas.
¿No? Bueno, no sé si hay una pregunta acá, alguna, por favor. Sí, profesor.
Encontré súper interesante la manera de perturbar los ratios de infección y los ratios de mejorarse en el fondo con una secuencia periódica. ¿Han probado quizás con otras sustituciones que tengan propiedades similares o qué tipo de resultados son similares a los que se ven acá?
Sí. Siempre se producen resultados cualitativamente semejantes, similares. I'll get back to English. In particular, if we look at these, this behavior here, if omega is larger than 0, always the relative noise for rho increases as t goes to the omega, and all different substitution sequences have different values of omega, okay? And it's always the value of omega suitable, like extracted from that periodic sequence.
Bueno, tal vez una última pregunta. el hecho de perturbar vía Fibonacci o otra serie, la dinámica, digamos, cómo voy actualizando, etcétera, se me ocurre la idea de que, bueno, normalmente muchos sistemas uno itera de manera asincrónica, que es tirar la moneda. En fin, ¿sí? ¿Qué diferencias habría en un sistema, por ejemplo, de autómata u otro, a tu juicio, entre la iteración asíncrona, tal cual tú lo trabajas, y una iteración, bueno, nosotros sabemos la diferencia con una palabra periódica, pero justamente con una palabra que no es aleatoria, sino que es aperiódica. Probablemente es interesante de medir eso. Incluso partiendo de la base de un autómata celular en una dimensión, está paralelo, asíncrono, etcétera. ¿Qué pasa si cambio el asíncrono, o sea, bajo la probabilidad en el fondo, y me llevo con un determinismo de una iteración periódica? Es que como eso lo que...
I never thought about that, but that would be a very interesting question.
Indeed,
you can choose to change aperiodically the rule itself.
of course. Okay, yeah. So,
Let's say two rules, you have two different rules, which have different tendencies, different fixed points, and what will happen if we
change periódico.
Yes.
Eso es. Yo no sé si hay otra pregunta acá o podemos pasar a... Se supone que tenemos... Se supone que hay comida. Muchas gracias.